Hi everyone, let me hope you are all doing fine. First things first. Last time we talked about an identity matrix. We also talked about the determinant of a matrix. Now, we almost coming to the end of matrices and we have about one discussion or two more discussions left. So today we want to talk about the inverse of a 2 by 2 matrix and see how we make use of the determinant of a matrix and how we make use of the identity matrix in defining the inverse of a 2 by 2 matrix. So it is really something very simple. Let me hope you enjoy this. So if A is a square matrix, then we shall write the inverse of A as 8 power negative 1. Okay, 8 power negative 1 denotes the inverse of a matrix A. Now, there is one important property about a matrix and its inverse. Okay, so we can write that so that if A inverse is an inverse, okay, is an inverse of A, then this is very important. If you get A and multiply it by its inverse, it will be commutative to the inverse of A times A, and this will always give us an identity matrix. This property is what we are going to exploit today to find the inverse of a matrix. Okay? If A is a square matrix, then its inverse is denoted as 8 power negative 1. Okay? And if you get the inverse, that inverse multiplied by that matrix, okay, it will, the order is not so important, but above all, you are going to end up with an identity matrix. So that is so important. Okay, let's see how we make use of this as we simplify or as we find the inverse of a 2 by 2 matrix. At your level, we only deal with inverses of 2 by 2 matrices. Other square matrices, the inverse, okay, you can find, but it is going to be somehow complicated for you. So UNEB will limit you to the inverse of a 2 by 2 matrix. Now, if I have a matrix A equals to 2, 3, 5, 8, that's my matrix A. Okay, then let A inverse, let's try to approach this in a simple way. We call it A, B, C, D. Okay, and we know that we have a property. If you get A and multiply by its inverse, okay, it will always give you an identity matrix. Here the order is not so important. Even if you begin with A inverse and multiply by A, still it will lead you to an identity matrix. So you just take one. Okay, don't have two choices. Just pick one and move with it, because the answer is going to be the same. So without wasting time, let's see, make use of this. A times A inverse. We have picked a matrix which is 2, 3, 5, 8. And we want to multiply this with A, B, C, D. But we are saying that this is going to produce an identity matrix, which must only have ones on the leading diagonal. So 1, 0, 0, 1. This is what we discussed in our third lesson about identity matrices. If you didn't really pick it so well, you can always refer. Just visit my channel, that this information is always there. What you need are just MOBs. All right. So let's multiply these two matrices, and then we equate corresponding entries, because the two matrices are equal only if the corresponding entries are equal. So we multiply. We have learned about matrix multiplication. Okay. So what do we get when we multiply here? 2 multiply with A, we get 2A. Then 3 multiplies with C, we have 3C. Okay, let's move on. 2 times B is 2B, and 3 times D, this is 3D. Okay, Then we have 5a plus 8c. Then here we have 5b plus 8d. Okay, this will give us 1, 0, 0, 1. Okay, so we equate the corresponding entries. What do we mean by equating the corresponding entries? What I have here must be equal to 1. This part must be equal to 0. Okay, down, this must give me 0, and then this must give me 1. Okay, so we equate those corresponding entries and see what we end up with. Let's begin with this first part. 2a plus 3c is equal to 1. Okay, let's also to make our life simple, let's look for another entry which is having a and c. It is here. It is 5a plus 8c equals to 0. And you guys have looked at simultaneous equations by any of the methods apart from matrix method. You have seen what we call elimination, substitution. Okay, so let me use elimination. If I want to eliminate a, I'll multiply the first equation by 5 and then the second by 2, so that I get 10a plus 15c equals to 5. Then down it will be 10a plus 16c equals to 0. Now we subtract the 2 and then we shall get c. Okay, so here I have negative c equals to 5. And what is c? C is negative 5. Okay, we divide through by negative 1 on both sides, and then we end up with the negative 5. So to get a, you substitute. Okay, substitute. If c is equal to negative 5, we know that okay, 5a plus 8c must be equal to 0. Okay, so 5 times a plus 8 into negative 5 must be equal to 0. So 5a minus, this is going to be 40. 4 by 5 is a 40. So let me take the other side. Is equal to 0 plus 40. And therefore, a is 40 over 5. What do you get if you divide 40 by 5? We end up with 8. Okay, so we have a equals to 8, and we have c is equal to negative 5. So what are we left with? What we are left with is something very simple. We're left with the b and d. Okay, so b and d, if you find b and d, then we have to make use of this other part to find b and d. You equate those corresponding entries. All right, let's get there. Straightforward. Let's go and solve these two. Okay, still to eliminate b, you multiply by 2, multiply by 5. Okay, let's multiply. 2 times 5 is 10b. 3 times 5 is 15d equals to 0. Then this is 10b plus 16d is equal to 2. Okay, do the math, subtract. This is 0 minus a d equals to, okay, you have 0 minus 2. What do you get? Negative 2. Okay, so if negative d equals negative 2, what is d? Okay, divided by negative 1. Okay, d is equal to negative 2 divided by negative 1, which is equal to 2. Now, to find the b, just substitute. Okay, pick any of the equation, is either 2b or 5b, whatever you want. Okay, 2b plus 3d equals to 0. I will say that from this equation. So I have my d is equal to 2. 2b plus 3 times 2, okay, equals to 0. And 3 times 2 is 6. So 2b plus 6 minus 6 is equal to 0 minus 6. Okay, what do we get? 2b equals to negative 6. And the b equals to negative 3. Okay, so let me now sum up everything here. We have A is equal to 8, B is equal to -3, C is equal to -5, and D is equal to a 2. So let's look at our A inverse. We called it A, B, C, D. So if you substitute for A, B, C, and D, you'll end up with 8. Okay, you have -3, -5, and a 2. Okay, so let's try to see if there is a relationship between this matrix and the original matrix. The original matrix was A equals to 2, 3, then 5, and 8. Okay, 2, 3, 5, and 8. Now, if you make a comparison, we want to get a formula for computing the inverse of a matrix. What we have gone through is a bit lengthy. So I want to generate a formula which will help us, find the inverse of a matrix so fast without going into the details of solving simultaneous equations. So let's try to analyze these two matrices. Okay, look at the original matrix. We had a 2 and the 8 on the Benja diagonal. And what has happened? 2 has switched a position, and the 8 switches and takes the position of 2 to get the inverse. Look at this, okay? 2 is here, and then 8 is up there in the inverse. So the 2 have switched positions. What about the secondary diagonal? If you look at this other diagonal, what happens if you check this with the inverse? Okay, look at this and also come here and check this inverse. Tell me what you see. Okay, you discover that the 2 didn't move from their positions, but they changed their signs. So there is something so important here. Okay, let's discover something more on the next page. Okay, something we want to discover that we can always make use of when you're getting the inverse is the determinant of the matrix. So this matrix A, which is 2, 3, 5, 8, you discover that the determinant of A is 1, okay? The determinant comes into use when we are getting the inverse. Here we are lucky, but each of these elements was supposed to be over 1, over 1, over 1, over 1, okay? But anything divided by 1 remains, so that one didn't affect. However, if we are dealt with a matrix whose determinant is not equal to 1, then it would appear, that factor would always appear down there, okay? If you want, I can try for you one example, but there is something we can conclude here. This is 1 over 1 into 8 minus 3 minus 5 and then a 2, okay? So if A is a matrix which is A, B, C, D, suppose, okay, that's a general matrix, then A inverse will always be 1 over determinant. That abbreviation is allowed, determinant of A, but it must begin with a small d, not a capital D. 1 over determinant of A into, now these elements here on the major diagonal will switch positions, okay? So we shall have D, okay, and the A coming down. Then these 2 on the minor diagonal will only change sign, okay? So this will be a negative C and this a negative B. So that's the easiest way of getting the determinant of finding the inverse of a matrix, okay? We make use of the determinant, and then this other part which we have just included here, this is called the adjoint. We call it the adjoint, okay? Some people call it adjunct. The same thing, but we shall stick to adjoint. So this is what we call the adjoint of the matrix, okay? Adjoint of the matrix is that matrix where the elements on the major diagonal switches positions, and then the elements on the minor diagonal switches just signs, okay? That means that if I have a matrix B, which is equal to P, Q, R, S, then, okay, the adjoint of B, okay, will be equal to, so this addition is also allowed, okay, is equal to, okay, P, these two elements here will switch position is, I will have S and the P coming down. Then these two only changes sign. So I have minus R and minus Q. That's the adjoint. And if you have to get the inverse of B, okay, what you do, you write 1 over the determinant of B times the adjoint, which is S minus Q minus R, and that's P. So it is easier to find the inverse by using this formula than going through the lengthy process of solving simultaneous equations. So this is what you should know, that to find the inverse of a matrix, it is going to be 1 over the determinant times the adjoint. Okay, and what is the adjoint? You have to know what happens if you have to find the adjoint of a matrix, switch the elements on the major diagonal, switch their positions, and then on the minor diagonal, just change the signs. So it is as simple as that. Now let's calculate the inverse of this other matrix. I think the determinant is not equal to 1. Let's see. So we have this question, it says find the inverse of matrix A, which is 1, 2, 4, 11, okay? I can use my shortest method, but I still want to show you that if I use the method of solving simultaneous equations, it leads me to that method. Then after this, I will always stick that method, because I don't want you to go through the lengthy procedure of getting the inverse by solving simultaneous equations. Though you can always do that, but you know, it's not time friendly. So I'm going to let my solution, okay, let me pick a different color, which is so let A inverse, okay, equals to P Q R S. So let's exploit this property of a product of a matrix and its inverse equal to an identity matrix, and we know that A by A inverse must be equal to, in this case, A is 1, 2, 4, 11, okay, multiply this by P Q R S. It should give us the identity matrix, which is 1, 0, 0, 1. This is a property of a matrix and its inverse. When you multiply a matrix and its inverse, it will always give you an identity matrix. Okay, so let's multiply. You know, this is P plus 2R. Then I have Q plus 2S. Then this is 4P plus 11R. Then I have 4Q plus 11S. This should be equal to 1, 0, 0, 1. Okay, so P plus 2R equals to 1. And the 4P plus 11R is equal to 0. Let's eliminate, you know, simple methods. Multiply by 4, multiply by 1. So you eliminate P. And here what do you get? 4P plus 8R is equal to 4. And then 4P plus 11R is equal to 1. It's equal to 0 rather, okay? Subtract. What do you get when you subtract? Okay, 4P, this is a 0, minus, this is a 3R, is equal to a 4. Okay, so what are we saying here? We are saying that a negative 3R gives us a 4. So R will be negative 4 over 3. Okay, R is negative 4 over 3. So if we have R as negative 4 over 3, we can go ahead and, you know, eliminate whatever. We have P plus 2R must be equal to 1. So P plus 2 into minus 4 over 3 is equal to 1. And therefore, P minus 8 over 3 equals to 1. Okay, so if P minus 8 over 3 is equal to 1, we can start P minus 8 over 3 plus 8 over 3 is equal to 1 plus 8 over 3. Okay, so this goes, and therefore P is 1 plus 8 over 3. Okay, you get the LCM, and that is 11 over 3. Okay, P is equal to 11 over 3. We have P and we have the value of R. Okay, R equals to negative 4 over 3 and P equals to 11 over 3. Okay, now that factor 3 which is coming down, it is so interesting. You see why 3. Okay, and we shall check it by calculating the determinant of A and see if it is equal to 3. So it is interesting. Okay, let's go ahead and solve for Q and S by the same approach of elimination. We're gonna get multiply here by 4, multiply by 1. Okay, what do you get? You have 4Q plus 8S is equal to 0. Then we have 4Q plus 11S is equal to 1. Subtract these two. Okay, 4 minus 4 is 0. 8 minus 11 is negative 3S is equal to negative 1. Okay, so what is S? S is equal to a minus 1. S is a minus 1 divided by negative 3, and that is simply 1 over 3. Okay, then we solve finally for Q. From Q plus 2S is equal to 0. So Q plus 2 into 1 over 3 must give you 0. So Q plus 2 over 3 equals to 0. Okay, there are so many methods of solving. You know, you don't have to cram mathematics. Some people multiply 3 by 3. Okay, let me use that. And I have 3Q plus 2 equals to 0. Some people just take the 2 over 3 directly to the other side. So Q is equal to minus 2 over 3. Okay, so we have the value of Q as minus 2 over 3. We have all the values. Let's summarize these values and bring them together. So here we have a summary of our results we have obtained from the calculation. Okay, you discover that solving simultaneous equations is one of the methods of getting the inverse of a matrix, but it takes a lot of time. So I want us to summarize this and then conclude on the formula, and always use that formula, because this will always take you through, a lot of time, and you lose out if you are answering a national exam. Therefore, what is our we had A. So let's write our A inverse and feed in the value of PQRS. You discover that P is 11 over 3, Q is minus 2 over 3, whatever, everything is over 3. And yet 3 is the determinant of the matrix A. Okay, so I want to pull it out, and I have this as 1 over 3. Remember, scalar multiplication of matrices. Each entry multiplies by, okay? So this is 11, this is negative 2, and this is negative 4, and this is a 1, okay? Now, check this and the original matrix, okay? What has happened is exactly what we have said in the previous problem, okay? This element switched a position and took up the position of 1. Similarly, one said, no, I'll take up your position since you have displaced me. So you have these elements on the major diagonal, okay? They have switched their positions. Then the elements on the minor diagonal, which is a 4 and a 2, they did not move, but the sign is changed, okay? So what are we concluding? To find the inverse of a matrix, you only need the determinant of the matrix and then the adjoint. Remember, this is the adjoint of a matrix. Okay, adjoint of a matrix means that the elements on the major diagonal or the principal diagonal will switch positions, and then the elements on the minor diagonal changes just their signs. Okay, you have the adjoint of a matrix, and now if you get the adjoint and scalar multiply it by 1 over determinant, then you end up with the inverse of a matrix. Let me hope this makes sense to everybody. You know, mathematics is going to be for everybody's consumption. For the next 200, 300 years, they will be learning the same things because new ones will be born as we go away. So let me hope this knowledge makes sense so that you pass it over the next generation. So this is the conclusion we are making for you, or I'm making for you as ordinary level students. Remember, it is applying to your level as ordinary level students. When you go to higher levels, we might devise some other method of getting the inverse, because we shall deal with the inverses of matrices that a square matrix and more than, 2 by 2, maybe 10 by 10. Okay, 10 is a big matrix, but maybe 3 by 3 or 4 by 4. Okay, right now at the level where I am, I can compute the inverse of a 50 by 50 matrix because we use it in cryptography a lot. Okay, so let me summarize this for you so that you can make use of it always. Don't go through the lengthy process, but if you want, it's up to you. So the summary is, if A is a matrix which is ABCD, having entries ABCD, then the inverse, okay, to find the inverse, just get 1 over determinant of A and then times the adjoint. Okay, so what you need is to get the determinant only. That's the only calculation which is performed, and then feeding in the formula. Let me give you this example. So we have this question which says, write down the inverse of the following matrices where possible. You know, there's a reason why they are saying where possible, and I will explain that in a short while. Okay, so let me work out this. I will just add on another question and work it out. So there is 2 minus minus 2, 3, minus 3, and then a 4. Okay, so okay, let me call this matrix P. Okay, so I get determinant of P. You know how we find the determinant? We get the product of the major diagonal minus product of the minor diagonal, which is negative 2 into 4 minus 3 into minus 2. Okay, 2 into 4 is negative 8, and the minus 3, then the minus 2 is plus 6. So the determinant is equal to, the determinant of P is a minus 2. Now, we want to get the inverse of P. P inverse is 1 over the minus 2 times the adjoint. The adjoint, we said, the elements on the major diagonal switches positions, and then the elements on the minor diagonal, which is 3 and the negative 3, will switch sign, and then we have 1 over minus 2 into. So if you want, you can multiply through, and you have 4 over minus 2, then minus 3 over minus 2, then down it is a 3 over minus 2, and then minus 2 over minus 2 if you want. Okay, and this will be a 4 over minus 2 is a negative 2. Then this is a 3 over 2, because negative divided by negative is a positive. Okay, this is a 3 over 2 negative, and then this is a positive 1. So that's the inverse of the matrix P. Lastly, on our discussion today, we discussed what we call a singular matrix. Okay, without wasting time, I'll start a singular matrix. Singular matrix. So a singular matrix has 0 determinant, and it will never have an inverse. Okay, let me use this example to explain why the inverse does not exist. So let P equals to 3, 6, 2, 4. Okay. Now, what's the determinant of P? Okay, product of principal diagonal minus product of the secondary diagonal. This is going to be 4 by 3, which is a 12, minus a 2 by 6, which is also 12. So this will be 12 minus 12, and the determinant will be equal to 0. Now, if we attempt to find the inverse of P, okay, then it will be 1 over 0 times the adjoint. The adjoint, this is 4, 3, negative 6, negative 2. Okay, so 4, 3, negative 6, negative 2. Now, if you look at if you look at this, okay, this is not defined. Not defined. The reason is 1 over 0 is not defined. We say it is infinity. Therefore, if a matrix has 0 determinant, that's the point of emphasis here. Every time we hear about singular matrices or a singular matrix, two things should come to your mind. The determinant is 0 and no inverse. Okay, so let's use this to solve our last problem today, and then we shall be left with using matrices to solve simultaneous equations. Then just general questions about matrices. I work for you some 4 or 3, and we call it a topic. So we have one more discussion after this. So here we have a question. Given that P, which is A to A minus 1, A plus 1, that matrix is a singular matrix. Then they want us to find the possible values of A. The solution is simple, okay? So if you are ready, this is not going to appear. This is not going to appear. Let me change the color and use blue. Okay. Solution. So we know that if P is singular, okay, it means that determinant of P is equal to 0. Now get determinant of P. Determinant of P is A into A plus 1 minus 2A into A minus 1. And this must be 0. Multiply A times A is A squared. Then A by 1 is A. Then minus, okay, 2 times, okay. Oh, let me just open it since you guys can deal with the brackets. So 2A by A is minus 2A minus 2, oh my, 2A squared plus 2A equals to 0. Okay, so we discover that this is 3A minus, okay, A squared equals to 0. And this is A into 3 minus A equals to 0. Okay, so my tablet is warning me, so I got to sign out. Now, this is a product, the zero property of products. If a product of 2 is equal to 0, then either of the 2 is equal to 0. So A equals to 0, or 3 minus A equals to 0. Okay, meaning that my A is equal to 3. So there are two values of A. A is equal to 0, or A is equal to 3. Those are the possible values of A. And we are done. So ladies and gentlemen, let me end here today. Technology is ruling me out. I think I'm also tired. Let's meet in our last discussion, and that will be the end of matrices before we go to transformations. Let me hope you guys are staying safe, and I wish you the best. See you. Make sure you subscribe, and don't forget to click on the notification bell. That way, if I upload a new video, you are notified instantly. Okay.